Dear students, in this video we are going to talk much about the some of the part of electrochemical machining, which is not covered in the PowerPoint presentation. So definitely this part, some mathematical part, we are going to cover in this video. We know that this is ECM, isn't it? So let us see some electrochemistry of this process. Okay, so we know all these things about the electrochemical machining, but the thing which we have not discussed, that we are going to discuss. Okay, so we know that the material removal is taking place due to the electrolysis, that we know, but what is chemistry behind that we should understand. So we know that in the quantitative form we can write the Faraday's law as this mass is proportional to the IT epsilon, isn't it? Now see here, where mass is what? The weight of the material, weight which is in grams of the material dissolved or displaced, isn't it, from the anode, that we know. T is a time which is in seconds, and epsilon is the gram equivalent weight of the material, gram equivalent weight of the material, which is equal to capital A divided by small z, where A is what? The gram atomic weight divided by valency of displaced ions, valency of displaced ions. Okay, and here in this Faraday's law we are having this proportionality constant. So if you want to remove it, we have to put this proportionality constant, that is m is equal to now IT epsilon divided by this capital F, and capital F is what? This is the Faraday's constant, Faraday's constant, whose value we know that it is 96500 coulomb per mole, isn't it? That we know very well. Now if I put here this value of epsilon, that is m is equal to AIT divided by what? This F times Z, isn't it? So this is the mass which is get dissolved at the cathode, at the anode, sorry, which is AI times T divided by F into Z. Now say if I take this T here at the denominator, okay, so at the LHS, if I take this T here at the LHS, what I can write? So I can write here, see, that m upon T is equal to AI divided by Fz. Okay, so what is this mass per unit time? It is the mass flow rate, isn't it? So I can write m dot, that is, it is a rate. This m dot is equal to AI divided by Fz. Very, very important. This is the mass flow rate in the ECM, which can be having the unit of grams per cc. Many times the questions are framing on this formula. What is that? The mass flow rate in ECM is equal to gram atomic weight into current divided by Coulomb's Faraday's constant divided by this valency of the ions. Okay, now let us see that suppose our anode is made up of the pure material and rho is the density of the anode. Rho is density of the anode material. Then what will be the material removal rate, that is represented by Q, will be what? This AI, that is mass divided by density. You will get the volume, isn't it? This AI divided by this rho Fz in centimeter cube per second. So this is your material removal rate. This is your material removal rate in the electrochemical machining. When the anode, that is workpiece, is made up of pure material, it is not made up of alloy. So what if the workpiece is made up of alloy? Then how to calculate this Q? Suppose this workpiece or the anode is made up of the alloy, and alloy, definitely alloy having the different materials in that, isn't it? And each material is having their weight percentage, isn't it? So in that case we can write this Q S, that is the specific material removal. Please remember, this Q is not the material removal rate, but it is the specific removal, which is equal to 0.1035 into 10 to the power minus 2 divided by density into 1 upon summation from I ranging from 1 to n, this xi zi divided by ai. Okay, where xi is what? That is the weight percentage of that element which is present in that alloying element which is present in the work material. Weight percentage of alloying element or material. Zi is what? Its valency, and ai is what? Atomic weight. Okay, for that element, alloying element. So it is valency and ai will be the atomic weight. And density, rho is what? It is density of the material, workpiece material, which is actually not a pure material, but which is alloy, which can be calculated by this rho is equal to 1 upon or 100 upon summation of I ranging from say 1 to n, this xi divided by rho I, which is in grams per cc. We can able to calculate first of all the density of that material or workpiece, then put here, and whatever the alloying elements that are present, their percentage, weight percentage, their valencies, their atomic weight, we have given with all this data. So we can able to find here what is this QS is the specific removal which is in centimeter cube per ampere per second. Please remember this. What is the unit of this? QS, specific removal, which is a unit of this centimeter cube per ampere second. And if you want the material removal rate, that is only Q if you want. So how to calculate? So for the with this specific removal, if you multiply by the current, if you multiply by this amperes or current, isn't it? Then you will get this MRR, it is in centimeter cube per second. Please remember this. So this formula is only for the specific removal. If we want the exact our Q, that is material removal rate, we can get this Q by multiplying with the current to this term. We will get in centimeter cube per second. So on these formulas, many times the questions are asked. Let us see one or two questions based on this. Which formula? This formula. this formula and our material removal rate for the pure material, pure anode, that is AI divided by rho times Fz. Okay, please remember this. And one more thing here that we want to know, that is sometimes here, suppose the difference between the applied voltage and the over voltage, that is say over voltage is represented by say delta V and say applied voltage is known to us, that is V, then we can able to find the density of current which is given as say J is equal to K times V minus delta V divided by this Y. Okay, so please remember, where this density of current is given by K into bracket V minus delta V divided by Y. So Y is what? The gap between this tool and the workpiece material. K is what? Thermal conductivity. Sorry, K is what? The electrical conductivity. We know that which is the reciprocal of what? The specific resistivity, isn't it? And specific resistivity is what? Is given as, we know that rho is equal to R times L upon A, that is R resistance in ohm, the length of the conductor is in centimeter and cross section area of the conductor in centimeter square. So it will be what? It is, फिर से लेना यहाँ से. So rho is equal to what? That is R times A by L. So R is a resistance in ohm, A is a cross section area of conductor, isn't it? And L is what? The length of the conductor, say in centimeter. So you will get rho as ohm centimeter. And K will be what? The conductivity will be ohm inverse centimeter inverse, isn't it? And you know that V is the applied voltage and delta V is the over voltage, and Y is the gap between the tool and workpiece. So this density of current we can get in the ampere per centimeter square. Ampere per centimeter square. If you multiply with the area, we can get the current, that is amperage. We'll get the amperes. So please remember this one more formula for the current density in the electrochemical machining. Okay, we will solve one question on this. Thank you.